Hello, everyone. Very welcome to this seminar. My name is Lyudmila Mikhailova from the University of Sheffield, professor, and I'm going to chair this afternoon's seminar and discussion. And it is my great pleasure to introduce you Professor Nidhal Bouaynaya from Rowan University from the US. She holds a PhD in electrical and computer engineering and an MSc in pure mathematics from the University of Illinois, Chicago. Currently, she is the director of Rowan's Artificial Intelligence Lab and is also the Associate Dean for Research and Graduate Studies at Rowan University. Her research is focused on statistical learning and trustworthy systems. Today, Nidhal is going to talk to us about self-aware artificial intelligence and lessons learned from optimal estimation theory. So very welcome, Nidhal, and it is over to you.
Thank you, Mila. So indeed, the title of my talk is Towards Self-Aware Artificial Intelligence, Lessons Learned from Optimal Estimation Theory. Right. So this is Google's AI, or Artificial Intelligence System, and it clearly thinks, or it classifies that this turtle is a gun, which is obviously a problem. Now, the picture, what basically the mistake that Google AI did, it's not a simple, let's say, misclassification. It is actually a general problem with AI systems. So let's take a look at the picture to the left. So that's basically a hummingbird. If you train a machine learning neural network system, then it should be easily able to recognize that this is a hummingbird. But if you do a minor perturbation, right, that is imperceptible to the human eye, which is the picture to the left, you add a minor perturbation to the left image, the hummingbird, you get the right image, it's still a hummingbird, because you're unable to see these tiny perturbations. But now the neural network is classifying it as a hammer. Well, same thing here. We have a rabbit or a hare, and with a minor perturbation, now the neural network sees it or classifies it as death. So these problems or misclassifications of neural networks are not only in the digital world, right? You take the image, the digital image, and we added some noise. We clearly manipulated this image such that it is imperceptible to the human eye, but these issues exist in the physical world again. So here we have a neural network, right, that classified. We have this man who is wearing these funky glasses, right? They're actually 3D printed glasses, well designed, but just a man wearing glasses. And the neural network now is classifying him as Mila Djordjevic. In case you don't know Mila, this is how she looks like. Clearly, if we are deploying a face recognition system, right, to recognize, certain people, right, suspects, then by wearing simple glasses, you would, you can easily fool the system. It's literally fooling. Same thing, actually, this is a stop sign clearly for us. Yeah, truly, surely there is some graffiti in there, but a human being would be able to see the stop sign and clearly stop. But for a neural network system, because of that graffiti was purposefully put in there, now it fails to see the stop, and instead it is seeing the speed. basically. So now a self-driving car would actually speed here. So here is a video for, let me see if I can run it. Yay. So this is banana, the video of a banana. So surely, as you can see, the classifier is recognizing that it's a banana. You put in there like some random perturbation is still a banana, but now we're putting a it's not random, it's a crafted noise. And now the banana that we're running in is a toaster. And so it's banana. Then I put, noise, then it's still able to classify it as a banana. And then you put crafted noise, and now suddenly it becomes a toaster, misclassification. So, so these manipulations called adversarial attacks, they're not only computer vision, they're actually in all systems. So here is a video, there also exists in speech. So here is an original speech. Let me make sure you can hear it. Share sound.
Without the dataset, the article is useless.
Obviously, the video says without the dataset, the article is useless. And if we have a machine learning system that transcribes the speech into text, then it will just write the correct text. But now we've attacked that audio. So listen to how the audio looks like here.
Without the dataset, the article is useless.
You do hear some background noise, but basically it still says to a human, without the data set, the article is useless. But actually, for a neural network, it now says, okay, Google, browse to evil.com. Right? So, so there is an issue, right? So, and that issue actually, if we go back to MS, we can see it. So it's the issue of being confident in erroneous predictions. And this is known actually even to the public as the brittleness of machine learning systems. So let's take from the MNIST data set, the image of 1. So this true digit is the digit 1. But as you can see, we did some manipulation in there. We didn't do a great job at hiding it because that's not the purpose. But as you can see, the neural network predicts it as 3. But now if you look at the output of the classification, 3 is obviously the erroneous prediction, yet the network has, I really don't want to say confidence, but if you look at this output as probability confidence, then it's 97%. It's telling you this is a 3 with 97% confidence, and whereas 1 has only 2% confidence. So whereas obviously it's wrong, right? So people have shown, so this is a sophisticated neural network, this is ResNet, that the accuracy of neural networks do not match their confidence. So people have done these huge studies. This is a 110-layer ResNet on CFAR10 dataset. And basically what you can see that the average, the graph to the left is from a paper, the average confidence of the ResNet is substantially higher than its accuracy. Right? That's basically what you see on the accuracy versus confidence graph to the right as well. Again, you see that the ResNet's accuracy does not match its confidence. And here by confidence is what you may think is the output of softmax in a sense, that probability vector output. Right? So what's the issue here? And is there any way to understand it or to at least mitigate it, not to fix it? So if we want to talk about confidence of the neural network in a decision, then confidence really refers to probability. But neural networks are actually deterministic entities. So we cannot really talk about confidence if we did not define probability over the system or the data or our space. And the output of softmax is actually only a probability that in the sense that it sums up to 1 and it's positive. But if you think about it, it's only the output of the network that is simply compressed and mapped in a nonlinear fashion in the interval 0, 1. That's it. It is not a probability in the statistical sense. So we need here to define probabilities in the statistical sense to get a good measure of confidence in a sense. Right? So obviously we do need to define good measures of confidence or equivalently quantification of uncertainty in neural networks. This could help many systems, including autonomous vehicles, autonomous systems. We all know about the issues, right, that came in Florida, later on, I believe, Arizona, from self-driving cars that actually crashed or got into an accident. Now, imagine if the sensors that are associated with the self-driving car, they don't give you a point estimate. This is a pedestrian, this is a red light, this is a red light, or this is a green light, or this is the sky. But in addition, they would give you a confidence level associated with it. They say, this is a pedestrian, but I'm not so sure, I'm not so confident. In that case, the control system, which is downstream of the machine learning system, would act differently depending on the confidence of the machine learning system. So that's the idea. Maybe the control would be modulated by the confidence of the machine, of the upstream machine learning system. Right? For that, we need Bayesian integrated within deep learning. Right? So with Bayesian, we're going to go from a point estimate, which is what current machine learning systems give us, to actually an entire distribution. That's what you want. So what's the difference between point estimates and a Bayesian? In point estimate, in current deterministic systems, basically, we have unknowns. They are treated as deterministic unknowns, and we are estimating them from the data. In a Bayesian framework, the unknowns become random variables with a certain prior, right? And then I have observations, that becomes my likelihood. And then all of the knowledge, when I need to estimate my parameters, all of the knowledge about my unknown parameters become in the, will be encoded or are encoded in the posterior, right? And the posterior, that would be the posterior distribution of the parameters of my model, right? Given my data. And that's the posterior, as we know from Bayes theory, is proportional to the prior times the likelihood. So then the problem boils down to, rather than estimating deterministic numbers, these are actually, the value of my neurons. I now would like to estimate the posterior distribution of my model parameters given my training data. Right? So what this means is that my neurons are here, let's say for a convolutional neural network, I took that example, I have a kernel, I no more have deterministic values, weight values that I'd like to estimate, but I'm putting a Gaussian distribution on top of that, so that at the end, I don't have a classification of my input in a sense, but I have a classification plus hopefully a measure of, a good measure, and I'll explain how good, of confidence of the model in this decision. Right. So mathematically, basically, my weights become random variables following certain prior distribution, P of omega. And given my training data set, right, that is X and Y are the labels, X is your data or labeled data, we are now interested in the whole problem boils down into estimating the posterior distribution of the weights given the training data. So why is that? Because if you have the posterior distribution, then you can actually find the predictive distribution of any new data point X star by simply marginalizing out the model parameters. And the formula is basically the predictive distribution of a new data set. You simply marginalize over the weight parameters, and you get a predictive distribution at the end rather than a number. Right? Now, the problem is, how do we get our posterior distribution, the unknown? That's the hard problem. And it is a high dimensional distribution. We have multiple layers of nonlinearity within the neural network. So how do we solve it? Well, variational inference is the most popular way of doing that, because it boils down the problem of estimating a distribution to an optimization problem. So variational inference simply says, I'm going to go to the next page and then show. I don't know what my posterior distribution is, or I'm going to say target distribution, but I'm going to have a family of parameterized family of distributions. Let's call them Q, right? And then in that family, I'm going to find the distribution that is closest to the posterior, right? Closest in one sense, so in this picture is going to be Q star, right? Closest in some measure, and we're going to take this measure to be the Kullback-Leibler, right? Measure, right? So my problem now goes down into minimizing the KL divergence between my posterior and this family of distributions, which we will call variational distribution, right? So if I write down the expression of KL divergence, and with some simplification, we end up actually with the expected log likelihood of the data minus the KL divergence between this variational distribution. Now phi is actually the new parameters. Once, if I know phi, the parameters of my variational distribution is the KL divergence between the variational distribution and the prior, and the constant that is basically independent of the weights, right? So what I'm after, the optimization problem, is minimizing this KL divergence, which is equivalent to minimizing the expected log likelihood minus, or plus this regularization term, just a regularization term. This is the picture. This is variational inference in a picture, basically. It's the closest distribution. We're happy with the closest of distribution to our posterior. Right? So yeah, so this is the variational inference framework, and it is, people will come and say, Bayesian, but Bayesian, is computationally expensive. Well, it's because of that expected log likelihood, right? The expected log likelihood is usually, even though variational inference, is the most efficient methods among all methods to do Bayesian within neural networks, right? Because others would rely on Monte Carlo, that's even more prohibitive computationally. But still, in variational inference, we find ourselves with this expression, expected log likelihood, right? And that's usually done with a Monte Carlo approximation, right? So basically, the expectation is approximated with a summation where these weights, right, are sampled from our variational distribution. Now the question is, can we avoid Monte Carlo while doing variational inference? And the answer is yes, we can actually show that we can approximate this expected log likelihood by the expectation over the variational distribution of the last layer, right, of the log likelihood. But it needs to be the distribution of the last layer needs to be propagated from the variational distribution of the first layer. So basically, at your first layer, you're putting distribution on top of your entire system. So your system becomes stochastic, right? Because your model is not optimal, right? Not in any sense, it's not optimal in the sense here, it's optimal architecture, right? And you're also putting distribution on top of your data. So here I have a posterior distribution at the first layer, variational distribution at the first layer, that I need to propagate forwards. And at the last layer, we can actually show mathematically that the expected log likelihood is approximated by the expected log likelihood of the last posterior. And then I would obviously forward back to learn the parameters phi. Okay. So we have a density we want basically from, that's training a neural network, right? We're minimizing, we do forward and backward propagation, and that's done using numbers. Forward propagation just compute the numbers, and backward propagation, you just do gradient descent to update your parameters. Well, we just replace the same process with densities. Now, the problem is, I didn't put here, the problem is that the non-linearities in the model. When you hit a non-linearity wall, we don't know how to evaluate in an explicit form or a closed form solution what is the closed form of a nonlinear function of even the simplest distribution. So that's why the forward part is really hard. I don't know what will be this distribution, because if I have two random variables x and y, right, even if x follows a Gaussian distribution, and even if f is my simplest nonlinear function, then I really don't know what's the distribution of y equal f of x, right? So that's where the whole difficulty lies. So we're going to solve that, and I'm going to show you a layer of methods where we're going to go from approximating to numerical full solution. So the first approximation is, I'm not going to forward distributions. I'm not going to propagate the distribution. I'm going to just propagate the mean and covariance, the first two moments. So here I approximated the problem from propagating distributions to propagating moments, because at the end, a distribution is equal to the set of its moments, all moments. But I'm going to just take the first two moments, mean and covariance. And we know we can simply derive that basically here, if psi is my nonlinearity, because the problem is when I had a nonlinear wall, and in general, if y equal f of x, then expected value of y at the first order approximation is approximately to f expected value of x. And we can also have a first order approximation of the covariance and of the variance of y, right? The various values of y, using the derivative of my nonlinear function. Right? So we can easily derive these formulas. And then we go back and we forward propagate using first order Taylor series approximation, the mean and the variance. In the back propagation, it is as usual, right? We use the gradient descent and we update these parameters. Now the parameters are going to be my mean and my variances and covariances. And as you can see, I wrote the last expression for the expected log likelihood term, right? The other term, which is the regularization term, also has a closed form solution if we assume that the variational density is Gaussian and the prior are Gaussian, then the KL divergence of two Gaussians has actually a nice closed form solution. Okay. All right. So basically, at the end, I have a stochastic system. My data is treated as a stochastic process, and my output would be my output prediction with its covariance matrix. And I'm going to show you in simulations that this covariance matrix is a measure, an exact measure of uncertainty, which means if you increase noise or if you are attacked, the variance values are going to go up and are going to go up exponentially high in a way that you can basically detect if you are doing misclassification, or especially detect if you are under attacks. All right. Now, can we do better than propagating moments or propagating the first two moments, or which is first order linearization, which I call really what we were doing is Kalman and extended Kalman. Can we do better than, by the way, by propagating means and covariances, what we are doing is just we're propagating Gaussians, right? In a sense. Well, yes, we can do slightly better using the uncensored transformation, right? So the uncensored transformation is a mathematical function, right, that is used to approximate what would be the result of a distribution when it has a nonlinearity, but only when this distribution is defined by its moments. And it's been mainly used with as an extension of the Kalman filter when we have a nonlinear dynamical system under Gaussian noise. Okay? And the distribution is usually characterized by its first two moments. Right? So how is it done? I didn't write the formula for it, but if you Google, the uncensored transformation, there is, the exact formula of how to create these sigma points, and then how to then these sigma points, they get transformed by your nonlinearity, here psi, right? And then your mean and covariance will be calculated as the sample mean and covariances of the psi of sigma points. So if you look at the mathematics of the uncensored transformation, it actually encodes a discrete distribution. And this discrete distribution is exactly propagated, through this UT transformation. So the main advantage of UT is that you are actually applying your nonlinear transformation because you're applying psi to every sigma point. We're not linearizing psi as we did with the Taylor series approximation. Okay, so but it still basically assumes that it's still deterministic because there is a deterministic way of generating these sigma points and then propagating them. The propagation is just given by the formula. The good mathematically, the uncensored transform is actually accurate to at least the second order approximation. So it is better than our first order transformation. And again, at the end, it's going to give me mean and a covariance matrix. I have the first two moments. We're still in moments propagation or first two moments propagation. How can we do better? Well, yes, the uncensored transformation is deterministic. We can make it stochastic. We can do ensemble density propagation. So, but ensemble density propagation would be really propagating Gaussian. So we're still under the Gaussianity assumption. And at the end, the mean and covariances are estimated using sample, the sample mean and sample covariance. Okay, now beyond Gaussianity, at the end, beyond, so far we've been doing only at the end mean and covariance, the first two moments. Can I get my entire predictive distribution, which I talked about early on, right? Can I get an entire distribution at the end rather than the first two moments? And the answer is yes, using the particle filtering framework. So in particle filtering, the basic idea is that we approximate our target distribution here, the posterior, with a numerical approximation with particles and weights, because that's what a distribution is. It's a set of particles that you sample from a certain space with their weights. So there is an entire beautiful theory of particle filtering. Its power actually stems from the fact that it's very simple to implement, yet very powerful because it does enjoy optimal guarantees and convergence properties to the optimal posterior distribution when the number of particles actually grows. Right? It's used in density tracking, and which is how we formulated our problem here, Bayesian problem, which is I'm now tracking densities across the network. Right? So I'm not going to go through the theory of particle filtering because basically you sample and then from a known distribution, but then you adjust the weights, right, using a very known formula that comes from the theory of importance sampling. And then you resample to avoid degeneracy, and then you have your estimate at the next step. Okay. So why did we do all this, basically? And how is this related to what I talked about early on, what my title suggested, self-awareness? So let's take any one of these methods. Let's take basically one of the first three. First order Taylor series approximation, propagation of mean and covariance, okay? And let's take MNIST, try to understand what's going on. So here, we took MNIST, right? There is no noise, it's noise free, okay? We took, this is the image of number 9, it was predicted at 9, but let's see in the framework of what I call extended variational inference, the name comes from the extended Kalman filter because of the Taylor series approximation. What we get, so the deterministic convolutional neural network is, okay, it's going to tell me this is number 9 and this is the output of softmax. Well, the my Bayesian framework also is going to give me the same thing. This is 9, right? But let's take a look at the covariance matrix, right? And let's take a look at the diagonal of the covariance matrix. So look at the diagonal elements. They are of the order of 10 minus 12, 10 minus 24, 10 minus 10. So what does that mean? Well, let's say that confidence is inversely proportional to variance in a sense, right? Or variance is actually my uncertainty quantification. So if I look only at the diagonal, we'll look later on at the off-diagonal elements. But for now, let's focus which diagonal elements are the variances associated with every class. So what the network is telling me that this is not 0, and I am very, very certain. My confidence is 10 to the power 12 certain. This is not a 1, and I am very certain. This is not a 2, and I'm extremely certain. And this is a 9, and I am very certain that it's a 9. My variance is 10 to the power minus 10. Or my confidence is 10 to the power 10. 10 billion is my confidence. Right. Now let's take the same number and we're adding noise here. It's low level of Gaussian noise. Right? And let's again take a look. So it still classifies it correctly, right? That's thank God, right? Some generalization ability, right? And robustness to low random noise at least. But take a look at 9 here. It went from 10 minus 10 to 0.5. The other values went from the order of also 10 minus 10 to, the order of 10 minus 2, minus 4. So it's still telling me that it's not 0, and I am, this confident that the 100 confident is definitely not a 1, etc. Definitely not a 3, right? The variance is low, and it's 9 with variance of 0.5 or with confidence, let's say 2. The confidence, remember, went in the other picture 10 billion to 2. We're adding more noise here, right? And now look at the values. Look at the variance of 9. It went from 10 minus 10 to 10. Like saying it's 9, but my variance is now 10, right? It's 8, but my variance is 0.5, etc. Somehow all the variances are increasing. So here, okay, even a higher level. Now the variance of 9 became 29. So does the variance of others. Of course, we can here look, it's funny that for 6, for 6, it's still very confident that it's not a 6. But, suddenly it may be confusing it with a 0 because the variance is 0.7, Okay. So same, let's take a look now we went to analysis, and I show you the curve, but I wanted to walk with you through, this analysis of the covariance matrix, but then I show you the exact curves of variances versus signal to noise ratio with all of the extensive simulations that we did. Let's take a look at adversarial noise now. So this is digit 1, but it was attacked with actually digit 3 to make the network believe that it's digit 3, and the attack level is FGSM. All attacks are almost, equivalent nowadays. So let's take a look at our network. This is the extended, variational framework, and this is the uncensored one. But basically, they behave the same. So the deterministic CNN, by the way, this is the picture that I showed you, is going to tell you this is 3 with, 97%, wherever that percent is. That's the deterministic CNN. Now, if we look at our uncensored, it's going to take you, okay, that's class 3, so you did make a mistake, but look at the variance. The variance here, actually, if you look at it, is the highest variance. So if you look at the variances, the highest variances are the one associated with the true digit 1 and with the digit that it classifies and it's mistaken. So here it says this is not a 0, but look at all others. This is interesting. It says it's not a 0, and I'm very certain. Variance is 10 minus 12. I'm very certain it's not a 0. It's not a 2, and it's very certain. Same for all others, at least up to 7. Same actually for all others. This is 10 minus 4, this is 10 minus 8. So the covariance, the variances are telling you, I am sure it's none of the other numbers. This number is telling you it's either 1 or a 3. That's exactly what it's telling you. Look at the variances. The variance of 1 is 139, and here is 109. And here it's telling you it's either 1 or a 3. That's what your system, machine learning system, is telling you. Same thing with the uncensored framework, by the way. But compare that with the deterministic system, which is telling you this is 3, 97%. All right. So now here are the entire curves. I plotted the covariances for you. This is the extended. We're going to just look at the extended. Same analysis for the uncensored framework, some analysis for the ensemble. We'll talk about particle filter later on. So we plotted the variance, the output variance, we call predicted variance, versus the signal to noise ratio. And we did this for Gaussian noise, that's in red, and adversarial noise or adversarial attacks, that's in blue. And we have to look at this in perspective of the accuracy, right? So as you can see first, for adversarial attacks, as the signal to noise ratio decreases for both, which means you're injecting more and more noise or attack level, increases, right? For both random noise, random Gaussian or attacks, your variance is increasing monotonically, right? And you can actually see that for random noise, you reach somehow a limit, but the variance increase for adversarial attacks is much higher. And by the way, we did this over a lot of data sets, not only UNMNEST and CFAR, we actually did this on real world data sets, on tumor segmentation data sets, on SAR images, on radar images, etc. So, and we observe the same behavior, that the variance increase for attacks is way higher than the variance increase for Gaussian noise. That's when we started investigating that we can differentiate actually between Gaussian noise and adversarial attacks, and hence, the self-awareness. But we need to look at this at the same time with the test accuracy. So basically, as you can see, at a certain level of SNR, your system is still generalizable, right? But at a certain level, as your accuracy starts to deteriorate, right, your variance is increasing very high, right? The same here, same analysis like CFAR 10 data sets here again. So the most important message here is that monotonic increase of the variance as we are injecting higher levels or higher doses of noise or attacks, and the variance increase for adversarial attacks is way higher than the variance increase for random noise. Okay, so that's pretty, I thought is very important compared to current systems that gives you a point estimate with no confidence, actually with brittleness. You definitely should not take the output of softmax as the confidence level. Now let's go to the particle filter, where now I have an entire distribution, not only covariance, right? I have a predictive distribution at the end. This is still work, in progress with Mila. So this is obviously, we validated everything we've done with the other approximate method, Taylor series, uncensored transformation, ensemble, etc. So again, if I have a noiseless 4, look at my distribution. So this distribution is over the labels, is over the softmax scores. It's basically, you have high confidence, high confidence interval. So the variance here as you can see, is very low. Right? So you're either around 0, most of your labels, like the numbers that are not 4 will give you something very low around 0. And the samples that predict 4, they are around here. Okay. As you add noise, you can actually see that your predictive distribution has a higher variance. So we at least validate that. We do validate that. We're still looking into the role of higher order moments here. Can the higher order moments of this predictive distribution, like third order especially and fourth order moment, tell me anything about the robustness of the system, its reliability, its trustworthiness with respect, even generalizability with respect to Gaussian noise or attacks? Okay? Or is it all we need is Gaussian? I actually may not need the entire predictive distribution. All I need is up to covariance. So we're still investigating this. Now, so far we did the analysis of the covariance matrix and we looked at the diagonal elements. These are the variances of the different classes. Let's take a look at the off-diagonal elements. Okay, in case of noise-free, Gaussian noise, and adversarial noise. In noise-free, look, I mean, it's basically the off-diagonal elements are all 0. So it's like everything is decorrelated somehow. At Gaussian noise, your matrix is all over the map, right? In terms of what's high, what's low. In adversarial noise, again, remember, the highest variances and covariances were only associated with what the network predicted and what's the attack. Like what is the real, what's the real classification and what's the attack classification. It's consistently, we find that, it's actually to the point that if we plot the number of test samples with the two largest variance values for adversarial noise, we can see that we have a peak. In the case of adversarial noise, well, here, you know, we have a peak at class 3 because the targeted attack class was 3. So we have a peak at the targeted attack class each time. We validated this through all benchmark data sets and in-house data sets as well. Whereas for Gaussian noise, you don't really get that peak. I mean, if you look at the values here, you look at the scale. So we are still investigating that, you know, threshold of variance when, you know, when it is just Gaussian noise, when it is an attack actually. But I think we don't even need to learn it or do anything sophisticated. We can just put a threshold in there. We say if your variance is smaller than this number, at least for comparable data sets, then basically you're safe from attacks. And if your variance is higher than that number, then you're under attack. The beauty about the framework it shows you here, by the way, is that at test time, you give your data sample, and at the output, you have at the same time both the prediction and the variance. Both. No other framework, I have to emphasize, does this. All other frameworks you do to estimate your variance or covariance, you have to do frequentist methods, including BBB. You have like to do you have multiple runs, Monte Carlo, and then a sample estimation of your variance. It is very important I emphasize that at test time, you get, it's a pair. It's no more a number, it's a pair at least, or it's an entire distribution, or it's a pair mean variance. So this is some of our results in trustworthy medical segmentation. This is the Bragg's data set, it's tumor, different parts of the tumor that we segment. So this is not a classification, we want to show that it works even beyond classification. This is segmentation, and the network here is UNet, right? It's the encoder-decoder structure. So this is the input image. You can see, you can see my, hopefully my mouse, and this is the ground truth, right? In noise-free, in one, that's your deterministic UNet or deterministic segmentation network. In two, this is the Bayesian framework where we do Taylor series approximation, or we propagate the first two moments, okay? And 3, now I don't have a variance or covariance matrix. I have an uncertainty map. I have a variance value at every pixel. So what we have is an uncertainty map. What you look at 3, that's associated with the Bayesian segmentation. So as you can see, most of the uncertainty, basically, this is the entire map, is at the boundary of your tumor, which kind of makes sense because it's at the boundary where, you know, even experts may disagree of where the tumor is. Now, if we also added Gaussian noise, right, to the entire image, then, you know, you kind of see how it deteriorates the segmentation when you add high levels of SNR20, the deterministic. By the way, we show that actually not only its ability to give you variance, the proposed framework, it becomes more robust to Gaussian noise. I think I didn't go carefully through the slides, but the accuracy at high levels of noise drop quickly for deterministic networks. It doesn't drop that quickly for Bayesian. It resists much, much longer before, obviously, if you are, you know, swimming in noise, or if your signal is equal to noise, of course you're going to fail. But it really resists much, much longer at much lower signal to noise ratios before dropping the Bayesian framework. So it's quite intriguing that this propagation of the variance of the covariance information suddenly makes the network more robust, even from an accuracy perspective, right? Generalizable, if you wish, to random noise. So this is the segmentation of the extended variational inference. As you can see, you know, here it made a mistake. This is self-awareness. Certainly, you know, this is your ground truth compared. Wherever it's making mistakes, look, now it's all uncertain about this region. It was actually very certain about this region in the noise-free case, and then suddenly it became uncertain. And now we do a targeted attack. I think we may be attacking with the yellow here, and you can see that, look at here. So it did make a mistake. This is not supposed to be the blue part of the tumor, but the yellow part of the tumor. But the uncertainty map already tells you. It tells you, well, I think this is the blue part of the tumor, or whatever class it is of the tumor, but you know, I am very, very uncertain about it. So take a second look at it. So the idea is like, take human, hey, take a second look at it. I am not so sure about it at all, as opposite to not having this uncertainty map, which is, here is my output. Whatever you do, whatever you want with it, just take it and run, or just don't take it, or you can or cannot trust it, not my issue, right? So we think that this is very, very useful in deploying machine learning systems in the clinic. Same thing, you're right, these are other segmentations for, these are radar images. So we have, again, the idea of uncertainty map, it becomes when we do segmentation, okay? And when we do attacks, you know, you can see basically from, I'm not going into details, but from left to right, noise-free, very little uncertainty, and then higher level of noise, more uncertainty, and higher, it becomes just more uncertain. So it's doing the segmentation for you, but it's telling you I'm uncertain, and then you verify that the regions where it's most uncertain are really the regions that are either misclassified, you know, or attacked. Right? And obviously, this is a work under progress. So we are still digging deeper, and this is the team, you know, behind working on different aspects of this work. From Mila, this is Dima. She was a PhD student for a short time postdoc. Now she's an assistant professor at Texas. Obviously, Hassan, Mila, and interns. Thank you. Any questions?
Nidhal, thank you so much for this inspiring talk and sharing with us your recent results. Yeah, indeed, time for questions.
Maybe comments or yes.
So thank you very much for the talk. I just wonder if the input is the image, how do you extract the mean and variance from the image?
Right. So the mean and variance, let me go back, is actually the output of the image. So hold on, here, for example, here, for honest. So this is the test time. I'm giving it this image one, which has been attacked, let's say, and the output, it gives me simultaneously the, your traditional output, let's say, right? The, I don't know really what to call them, the output of your network, right? It is compressed in the interval 0, 1, but at the same time, it gives you the covariance matrix. It learned this. So why it gives you that? Because it's in the, let me go back, it's in the your objective function. Your objective function is no more cross entropy, the simple cross entropy. So your objective function has sigma in it. This sigma y, by the way, this is the last layer. It has the this is only the expected log likelihood term. There's another term, regularization term. But now your objective function has embedded in it your mu y, which is your usual vector mean, but it also has your sigma y. It's the variational objective function. It's no more just cross entropy, although the expected log likelihood is, you're in the deterministic case is your cross entropy. But in this framework, remember, we we formulated the framework so that the problem is minimizing the KL divergence, no more cross entropy. And then that KL divergence became the expected log likelihood, which is this one, and plus a regularization term, right? Yeah, this is what you are minimizing now, it's this term, right? So you can go ahead and, the expected log likelihood term is, you can do it in a simplistic Monte Carlo approximation, of, these, then you will have to draw samples from all of your weights, or you can do density tracking propagation. Right? Yeah.
Thanks, Nidhal. Yeah, it's fascinating stuff. I think, if I understand it properly, the Gaussian approaches to these neural networks, we can look at the uncertainty on all the parameters in the network.
Okay.
Right. Is there any value in doing so? Given that we have this idea of convolutional and resonance and the like, where we can say different parts of the network are doing different things, is there value in understanding how the parameters, the variance on different parts of the network?
You have a great question. So first, let me emphasize the variance versus SNR. All the results that I showed you, the covariance matrix, is what I call the predictive covariance, right? Is your output.
Yeah.
Right? But yes, I have actually put a Gaussian distribution on every kernel here and on every neural network here. So I actually, can go back and correct. So I'm just propagating, mean and covariance. So I have the mean, but I also have the covariance of every weight. So it's a work in progress. We didn't look at the covariance of the weights themselves, but I'm linking that to the explainability. But because obviously I noticed that this Bayesian network became suddenly more robust to noise and attacks, besides the fact that it gives me the uncertainty estimation, you can actually show that it collapses way much later than a deterministic network when you keep injecting noise or attacks. We think that it's seeing something else. It's seeing more robust features. We have to define robust, and it's the same for adversarial attacks, right? It does resist them, which means somehow it's extracting, not seeing, right? If it's a CNN, then it's extracting your features. It is extracting better features than a deterministic network. Now, for that, we have to link that to explainability. So we're still, yes, we did not look at actually, early on we did, and then, yeah. So one thing we noticed, and we have a paper on this, is the self-compressionability. I have a student who is here. So we noticed actually that if you leave a redundant architecture, so we took a redundant architecture for MNIST, we did these experiments, and we noticed that many neurons and kernels become zero, very small compared to other kernels and neurons, very small. So what we did is, they're zero anyway. So we took off these neurons. So we simplified, we compressed our neural network, and we get the exact same results. And that's, we call it self-compressionability. So we do link that actually to continual learning or learning on the edge. And now you train a neural network, but to deploy it on the edge, you have to simplify it. Compression, you do quantization. So what we notice is that these Bayesian networks can tell you what to remove and what to leave. And that's by looking at the covariances of the weights, the self-compression ability.
Great, thank you very much.
But I agree, there is a big missing piece, I guess, it's work under progress about why it is, what features is it extracting, and why is it correct this robust? And that's where, so explainability, continual learning, and uncertainty quantification, I know they are not three different topics. They are all the same.
I wonder if it might also inform transfer learning, is what I was also wondering. Because obviously you train on one set, extract the features, and if you know the variance on the new set, it might give you some evidence of why it can be used in transfer learning.
Yes, yes.
Or
in continual learning.
Yeah,
Absolutely. Continual learning. Yeah. Yes, Ryan?
Thank you for the very nice results. I wanted to ask if you have explored the all opportunities for exploiting these results in a deployed system. If I know that I'm dealing with an adversarial attack, if I know that I'm dealing with noise from observing these covariance matrices and their values, is there anything that can be done to mitigate that situation? I don't know, maybe have a secondary network that's more computationally expensive but more resistant.
So if I understand your question correctly, if I don't answer it correctly, please pose it again. But yes, we are looking into discriminating random noise from attacks. Mm-hmm. And these are the last graphs that I showed at the end. I mean, yeah, these are the graphs that I showed, correct. So here, the discrimination is not these graphs. This is the variance. Yeah. So correct. Discriminate, figuring out that the system is under attack. So current systems, like state of the art now, a neural network cannot figure out if it's under attack or not. Right? Just give it data and it gives you output. It is what it is. So what we do is we put upstream a system that would detect attacks. So a system that tells how legit or how trustworthy is your data. And then if your data is legit, you pass that to your machine learning system. And if it's not, you throw it away or you give it to the human or you ring an alarm, right? But it's basically two systems. Here, I have a network, you give it data, and from the variance, correct, the ultimate goal is to say, I am under attack. Is directly ring the alarm.
And do something about it.
And do something about it. So either we are investigating, the doing something about it is, let's say, in self-driving cars, the control needs to be modulated by the variance. Right? The control, right, takes as input is the output of the machine learning system, feeds the control, right? So it shouldn't be just the decision or the output of solvents. It needs to be the variance. The control needs to take into account the variance as well. I think that's what we show. Now, back to when we are under attack and when we are not, we are investigating different methods, whether we can just put a simple threshold for different data sets. We saw like a threshold would work, or let's say for most of medical imaging, the same threshold even for would work. If your sigma symbol is small than this number, than sigma naught, then you're not really under attack. If it's bigger than sigma naught, then you have high chances to be under attack, really. Or we can actually learn it. This threshold of when or when not you are under attack. But it's work under progress.
Very, very interesting.
Yes, I get you.
Thanks for the talk. So I'm going to talk about the symbol karma framework. So I think each steps, if I understand right, before it's propagated, you generate in symbol models, and at the same time, this covariance matrix, or somewhere called karma again, to update it. So can I ask normally, how many, in terms of this in simple model, let's take example of the medical segmentation. Normally, how many in simple models you need to generate?
So you're talking about ensemble or
Yeah.
the particle filter?
In simple one.
In ensemble one, we actually have the sensitivity analysis with respect to the number of particles. I believe obviously the accuracy increases when the number of particles increases, but after a certain point, so in the beginning, the increase is exponential. Let's say you go from 10 points to 100. The increase is exponential, and then let's say after 1,000 points, I don't recall the number, the increase becomes really logarithmic. So you don't gain a lot from adding way more. So you actually have the ensemble is published. I can send you, the paper, and we do the analysis with respect to the number of particles, samples, I call them. Same with the particle filter. So the particle filter also, mathematically, you show actually convergence in at least two subsets, the expected in the RMS, I think, convergence, and we have convergence in distribution when the number of particles increases. And experimentally you show that for large enough n, I mean n equal 100, worked well for the benchmark data set. If you get ns, even for CFAR 10, for CFAR data set, it works well, n equal 100. Of course, it's a trade-off between accuracy and computational complexity when it comes to the particle filter. Right? Now, again, the particle filter is if you want an entire distribution at the end, but a more efficient method, if you want just mean and covariance, you just do the extended variational or the Taylor series, the propagating the mean and covariance. And that goes very fast because the number of parameters that you add is not a lot. By the way, it's not really the covariance matrix of all the weights. So we assume that the layers are independent, right? And if it's a convolutional layer, I assume that the kernels are independent. And you know what? It's not only not a bad assumption, it's actually, I think it's desirable because you want the kernels to extract independent or at least decorrelated features. So we really do not want, so then you only have a covariance for every kernel, right? Or for every fully connected layer.
Okay.
And then that is very fast.
Okay.
So, I mean, I think forget the particle filter, which is, again, it gives you an entire distribution. The three other methods, the Taylor series, uncensored, and ensembling, they don't give, they give statistically close results, in a sense, very close. So the uncensored is slightly, more accurate, at least in the data set that we saw, that the Taylor series, same for ensembling.
Okay.
So I would say the Taylor series would do the job very quickly.
Okay. Okay. Actually, I just want to ask. So, for instance, we're talking about this in symbol framework because if I understand right, it's kind of to reduce uncertainties in the process. So, by using maybe introducing some confidence intervals when we generate these symbols. For instance,
it gives you the entire covariance matrix.
Yeah.
So the ensemble of samples are there to estimate the mean and covariance. So imagine, so here, I am propagating, as you can see here, I want to propagate entire distributions. Let me go back.
Because this is Gaussian, so if you have an
Yeah.
elements,
Yeah.
you can recover the distribution.
So ideally, I am propagating distributions, right?
Yeah.
And then, because the problem is hard, we boil it down to propagating mean and covariance. So those particles, it's almost like you're propagating Gaussians, because at the end, you're going to take the mean and the Gaussian, the mean and covariance, sorry, and then sample over that and propagate. So you're just propagating Gaussians again. The only framework when you get rid of the Gaussianity assumption is the particle filter. Then you're actually propagating, it could be multi-model. One of the things that we are looking at is the multi-modality of the variational posterior. All other framework assumes unimodal, not necessarily. If it's multi-model, then the higher order moment may play a role. So we're still looking at that, with Nida She's part of this work as well. Yeah, I don't have an answer, but it could be that Gaussian is all we need. And in that case, we will write a paper called Gaussian is all we need.
Maybe Gaussian is good enough.
Yes. You had a question.
So again, thank you so much for the talk. It was really fantastic, and there's so much I want to discuss. But one of the questions I had is actually very similar to what Radi was saying, because as you were saying, at the end, you're like, oh, we have some sort of threshold, then we can determine if we are having an adversarial attack. But it also looked like to me that, and I highly suspect it's me missing something, I can only apologize, but it looks like to me as well from what we saw here today that not only can you figure out that you're going to adversarial attack, that you also could, with some degree of confidence, know what the class was actually meant to be beforehand. So like in the first few covariances that you showed us, and it's really, really fantastic that not only does it show you which ones it's not confident that it's classifying correctly, it's also very confident knowing what it's definitely not.
Correct.
And so at the very end, when you showed us the covariance matrix for saying, oh, it's trying to attack label 3, then once you know it's 3 and you've eliminated that as a possibility, then you could go back and just saying it's 1.
Correct.
So
it can self-correct.
Right, exactly. Yeah. So I was just sort of intrigued if that's something that
For adversarial attacks, we consistently show that the covariance matrix looks like this. By looking at the off-diagonal element, the highest ones are consistently, so here I believe we attacked with 3, so that it's a 1. So first all the variances are high because it's under attack, so it's unsure. But we consistently show that, I have to remember, right, this is for which example we attack. But yeah, the highest ones, 1 and 3 there, and 3, but here, I wonder if it's the same, the same graph. Here I see it's very high, correct, at 3.
If you look at the numbers,
Correct, it was 1 and 3.
Sorry. 1 was the second choice. So what you're
Correct.
saying is true. You throw a 3,
and
your highest number after 3 will become 1.
And that's
Self-correct.
the thing I'm sort of intrigued about is can you guarantee that would work for outside of the
No.
Okay. I won't use that word anymore. I won't use that word anymore. That and COVID are out of
Of course we can hear.
So no, you ask a very good question, and the answer is this is not something we can prove mathematically. So what we did extensive simulation. That's why, correct. That's
So you're
why.
talking about the upper one.
Yeah,
So
yes.
if you look at the statistics, 3 is 0.84. So if you throw a 3, your next obvious one is number 1, which is the correct answer.
So if you look at the variances, the highest variances are associated with 1 and 3. All others are actually very low. Again, this is a miss, but we did it for CFAR, we did it with others. So the idea is the variances consistently by doing experimentally, we found that, you basically, by only these two, they are really orders 10 to the power 4 higher than any other variance, then, literally, unlike for Gaussian noise, they are not 10 to the power. We don't find 2 that are 10 to the power 4. So we're still looking at these values, but also you want to look at the covariance between 1 and 3. They are the highest here. So we can exploit this knowledge. We exploit this knowledge to detect attacks.
I have a kind of a follow-on question from both of those, which is, do you have any thoughts on what I think is a very interesting field in this region, which is outer distribution, i.e. none of the above?
Okay.
So what have you
Mila.
found with that?
That's exactly what, there is fusion coming up, and that's what we want to apply this for out of distribution and submit to fusion. Mila, right?
Well, we can do something else. In addition to what Nidhal just presented, and there are results in premium CNN is, this is actually published and the code is on GitHub, but we've been working on something else, kernel filters, or called Gaussian regression, which may have different ways to representing the mean and variance or higher order moments. Actually, this is part of an NSF EPSRC project, which is actually towards the end. It's really great, the opportunity also to have Nidhal's visit through GRIP. But what I'm saying, there are other ways of propagating a distribution. As I said, we've been looking into kernel methods. They also need learning. And then through the kernel parameters, we can characterize whether the classifier or the segmentation works well and how much we can trust it, or any other solution. Even we can take in a simplistic form the sample mean and sample variance.
I'd be very interested to read some of that if you can pass them through.
It is indeed our proposal. So to answer your question, that's exactly what we are doing out of distribution data, this framework, to see if it works. My suspicion is, and my intuition says it should work, but yeah, we want to submit this to Fusion actually. And what Mila said when we wrote this proposal, right, Mila is correct, it's all uncertainty quantification is leading the Gaussian, what are they called? The
Gaussian process regression.
Gaussian process, thank you. The word process just skipped me, a long day. Gaussian processes, and you know, I'm leading the
which is actually a generalization of a Gaussian distribution. It is yeah, you propagate like a tube distribution over functions, and then you have the whole interval to which the result can belong to. And there are lots of similarities at the level of ideas between Gaussian processes and neural networks. Just the way the implementation is done is different.
Yeah. Yes, I've read a little, but not nearly enough.
So, but I think if, you know, to summarize is, by propagating variances in addition to means, we definitely showed through extensive simulations that the network becomes more generalizable, more robust. That's number one. Two, it can, so more robust to random noise, random Gaussian noise, and adversarial attacks. And two, we can leverage the covariance information to do a lot. I mean, one of the examples here I gave is leveraging it to see when the network makes a mistake, the network becomes unbalanced. When to detect adversarial attack, it could be leveraged to do that. But I think beyond what I showed, it could be leveraged for continual learning, for out of data distribution, for a lot. So I think all work, at least in my lab that I'm doing, whether in continual learning or others, we just use Bayesian network. We use the Taylor series approximation, mean and covariance. I just cannot have a machine learning system just give me a point estimate. Yeah, so let's go from point estimates to at least 2 moments. That's if I succeed in this talk, I'm really pushing towards. And computationally, again, we showed in our, so the first order and the uncensored framework are published in the IEEE transactions on signal processing. So it's available online. Forgot my train of thought. Yeah, but basically, I really want to push the community that we start, this should be our machine learning system, mean covariance, not just, you know, the mean. So that's, you agree with me on the summary, Mila?
Sure, even higher order moments, wherever it is possible.
Unless all we need is a Gaussian.
Unless, yes. Yes, but we have heavy tails in many cases, and yeah.
The network is learning. If you inject noise, forget what David said. I still take it simple. Injecting noise, and the network is seeing all of these numbers. You think the network is robust because it's learning that there is noise?
So we're injecting noise after it learned. It already learned the network. All these results are at test time. They're at the network finished learning, and when the network learned, it actually learned from clean data. By the way, I just trained the network here on clean amnests. It learned. I have already the optimal parameters. Now the network becomes a system that is ready to deploy and to give you predictions. So here, but now it's not going to give you one prediction, it's going to give you a couple. It's not learning, it's predicting for you. Now we're at test time. This is all at test time, but a good point that you bring, it learned from clean data. I never exposed it to adversarial attacks or to inject it. So this is the prediction it's giving you.
Right.
It's telling you, it's telling you it's actually 3, and it's giving you this variance, which means it's telling you my uncertainty about, it's either 3 and 1, basically here. If you look at the covariance, if you look at the variance element, it's telling you, well, here, 3, but, it's either 3 or 1. That's exactly, if it's speaking, it will say this, right? Compared to this, that's what we have now. I had a question.
Oh, yes. Well, it's very interesting. And I was thinking, if this is made when the DNN has already been trained, then this variance is telling me how much it deviates from the data it has seen. So would it be good to say that this variance is a metric on how good my network has learned from my input?
So it's a good question related to his same question. I cannot claim that because I'm testing it on, well, it is attack data. So in a sense, it is an out of distribution data, right? I mean, it's attack data. It's not like, it is not. So yeah, so it is on attack data. So to be fair, I cannot answer your question because I didn't test it on out of distribution data yet. But it is what we will be doing actually now. But it's a quick, it's an easy experiment to do. But all, I can bet you anything that, I believe we will have very similar results for out of distribution data. It's gonna give you some prediction, right? Like it's the output, its mean is not very different from the deterministic mean. This gives you most of the information, right? It's gonna give you some prediction, right? But I bet by looking at the covariances, you would see whether you should trust it or not. It's actually telling you when to trust it and when not to trust it. This is at test time, and it's so my hunch is yes, it will work on out of distribution data. Did we test it? Not yet.
But this is at test time when you're analyzing the whole network.
So at test time, I have a trained network, so I give it an input. And the network, it gives me prediction. Now my network becomes, it's my AI, right? I give it an input.
At this time, it's a matrix.
Correct.
Right.
So I give it, correct, it's one forward pass,
Right.
correct.
There's no network at this.
There is a network, correct. That is my matrix.
But it's just doing metric multiplications.
No, there is no linearity. You still have to do your forward pass.
Right, but you're not. Right.
Right. You still do one forward pass at this time.
Right, but you're not doing backward pass.
Correct. I'm not doing, but the backward was to optimize. The backward is really great in descent. I'm finished my optimization. It's one forward pass. So basically the weights are known and fixed. By matrix, we mean the weights are fixed, but it does one forward pass, that's it. And that's at one forward pass, it simultaneously gives me these two. I'm not sure if we have from the online audience or any comments or feedback. Mila, have you been monitoring the online? I think
Sure, but I don't see any questions in the chat.
Okay.
And I think we are a bit after the 1 hour. I can see some people yeah, they are teaching or other things. Maybe we can just wrap up a bit, 1 or 2 more questions.
Yeah, I think we can continue with
Yeah,
our
I think we'll
group.
continue the discussion in the room if no more questions.
Yes, I think that's and we'll continue tomorrow in when we have our meeting.
Yeah. Yes, Mila.
Okay. Okay, so thank you for the interesting talk. And to me, there are many questions. How to characterize uncertainty of a system? What would be the best function? What we are saying? Yes, the mean and the variance is one way which the variance characterizes the dispersion or the how far we are from the exact solution, but we can think about possibly other functions that can do that, and especially in real time when a system is working, a UAV, an autonomous vehicle are some examples, and learning, which brings us to explainable AI, not just learning AI, but to understand why is the system behavior in one or another way.
Absolutely. Just one thing I want to make, this is real time. This can be used just like a neural network, can be deployed in real time. These results are real time. You just don't get a point. You get a point and a variance, if you wish.
Yep.
It is real time. So it could be used for, yes, it could be leveraged for real time control, yes. But yes, all other points are indeed, well taken. So explainability of this type of Bayesian neural network is what we are doing also. So how are the features extracted different from a deterministic neural network? How are they more robust? How can we quantify or analytically write the rules for what's robust feature and non-robust feature? So there is some work in there, but the link with Bayesian hasn't been established.
Yes. So these are really important and not only interesting questions. If making contributions to them is a big thing. Okay. So let me thank you all, especially Nidhal and everyone, and Radu and Colin. I don't see you, but I can see a lot of interest in, and see you face to face during one of our next meetings, hopefully.
Mila, thank you, Mila. See you soon.
Thank you. See you soon.
Okay.
Bye for now.
Bye.
Bye.